Hello, friends. Today we have an amazing guest with us, Gerald Pollack. We are honored to welcome Professor Gerald Pollack, a renowned scientist and innovator in biophysics and water science. Based in the University of Washington, he leads research on the fundamental principles of nature, often challenging conventional scientific paradigms. Professor Pollack is the founding editor-in-chief of Water, the multidisciplinary research journal, and the founder of the annual conference of the physics, chemistry, and biology of water. His contributions to science are recognized internationally, and he received numerous awards. As a passionate advocate for transformative science, Professor Pollack leads the effort to reform research funding system, promoting high-risk, high-reward projects through initiatives like the Institute for Venture Science. Professor is known for his ability to explain difficult scientific concepts with clarity and simplicity. Today, we'll explore these groundbreaking water science discoveries, unique philosophy, and their impact. Welcome, Professor Pollack. It is our honor to have you with us.
It's my great pleasure to be with you, and I'm looking forward.
So, water is such an amazing and seems to be familiar substance for all of us. But what initially drew your attention and inspired you to get deeper into studying it?
For a couple of decades, I had been in a completely different field. We were studying the molecular mechanism of muscle contraction. And in that endeavor, I learned a lot about the sociology and politics of science. The prevailing viewpoint had been that the contraction of muscles at the molecular level, that operate in a particular way, and the idea of that was put forth by a distinguished, I should say, extremely distinguished scientist, Sir Andrew Huxley. And Huxley had won a Nobel Prize for his previous work, and I came to realize after a couple of decades of doing research in that field and challenging the great master, because the theory, I'm not sure exactly how to put it, but it's simply out of accord with the evidence. And I learned because I found that people in the field were not so much interested in the facts. They were more interested in getting the approval, being anointed by the great master. And so I even wrote a book on why the prevailing theory is wrong and what might be a better theory. And I found that the book was purchased by practically every researcher in the field, but I think it was read by none of them. I remember an interesting incident of walking into the office of one of those people, and I noticed that my book was sitting on the bookshelf. And so I pointed that out, and he pulled out the book, and he opened the book, and it cracked as it opened, as though it had never been opened before. So I began to understand about the sociology of science, and it has to do with dominant people, and researchers in the field tend to be obedient to figures who are as important as he is. So anyway, I was invited one day to a conference, and the conference had to do with a famous Hungarian scientist who had passed. This was a memorial conference, and the guy's interests were muscle contraction and water, and he too doubted the theory of muscle contraction. So I was drawn to the conference, and I gave a talk, and I think it was reasonably well received. But what intrigued me is the guy who I met, who was talking about the water inside the cell. Now, I had no exposure or interest to water at the time. This was 25 years ago. But I was compelled. First of all, the person involved, his name was Gilbert Ling, Ling. And Gilbert had come from China. After World War II, the Chinese government decided that they were going to send some of their most promising scholars to the U.S. to further their studies. And in a 2-year period, starting in 1948, they invited 4 scientists in physics, chemistry, biology, and 3 of them won Nobel Prizes. And the fourth one did not win a Nobel Prize, and I think it's maybe, but he was of that caliber, clearly. I think he didn't win a Nobel Prize because his ideas were too revolutionary. And as I began, I understood what happens. Revolutionary ideas are not broadly embraced by people in the field. They prefer their own ideas or the ideas that they're familiar with. So I see you're nodding your head and understand. So I kind of understood that, but I was absolutely blown away by Ling's presentation. He was saying that the water inside the cell is not like liquid water. He said it's more like a liquid crystal, although he didn't use that term, in which the molecules of water are organized, or he used the term structured, like soldiers at attention, something like that. So each water molecule, which you could consider, for example, as a dipole, plus like a little bean with plus at one end, minus at the other end, and because of those charges, these beans could easily stack upon one another, and the idea at first sounded unusual, to put it mildly, but he presented evidence one after another showing that his idea had great merit. Well, I left that meeting with my head swimming. I thought, this is so interesting. And also, besides his presentation, it was at least a half dozen other people who had evidence to support this point of view of Gilbert Ling. Well, as I said, I was blown away by this unusual idea. And just to test myself, because I'm blown away more easily than most, I gave one of his books to a few of my most promising students or postdocs. I said, please read it. Tell me what you think. And they came back to me, and their responses were pretty much the same. They said, this is such an interesting theory, and the evidence that's presented in the book is compelling that this guy is really onto something. And if he's right, all of biology is wrong, because all of biology is based on the idea that inside the cell, the water is just ordinary liquid water. And he's saying, no, it's not. It's more like a crystal. So my spirits were buoyed, and I thought, this is so important. And I've made my contribution in muscle. I was really enjoying myself, but I knew that it doesn't matter what we find and how many experiments we have, people are not going to pay attention. And so I was prepared to change fields, and I came to the point of realizing that, first of all, I don't have money to hire people to help with studies of water. It took a while. We finally got to it. But in the interim, I decided to do something, a sort of humanitarian effort. Gilbert Ling's books, they're so deep and penetrating, but also not easy to read. I think if I can imagine how Gilbert Ling writes his many books, he sits down at the word processor, or before that, the typewriter, and he bats something out and he sends it off to the publisher. The word editing, I think, had never crossed his mind. Or maybe the word editing doesn't exist in the Chinese language. I'm, I'm not sure. So I decided what I can do, what I prepared to do, is to write a book that conveys Gilbert Ling's ideas in a way that could be understood. And I did it, and the book received mixed reviews. Some people said that, oh, this is Gilbert Ling, and everybody knows that Gilbert Ling is a crackpot, so pay no attention to it. To at the other end of the scale, a well-known cell biologist from Harvard, and therefore we need to pay attention to it because it comes from Harvard University. He wrote this book. This is a 304-page preface to the future of cell biology. So that one I like better. Anyway, soon we were able to scrape up some funding, not easy, to study this exceptional, what I thought was an exceptional idea. And that's how we got started. And we just to a quick summary is to say that we were able to confirm that the water inside the cell was different from ordinary liquid water, but we found that Gilbert Ling's idea of stacked dipoles was not correct. And what we found eventually, I think, has a good deal of impact. So I'll tell you more about that if you ask me. But anyway, that's how I got started.
Wonderful. Yeah, thank you very much, Professor Pollack. That's a very interesting intro. And, like just for me, it would be very interesting to hear if you would, in a short, I don't know, give a short description. What is water? What is your current understanding of what is a substance?
Well, okay. So my current understanding, or our understanding, myself and people in my lab, is that there is such a thing as ordinary liquid water, and it consists of molecules that are bouncing around randomly at a fierce number of times per second or even per femtosecond. That certainly exists. But inside the cell, inside a healthy cell, the water does differ. So our first experiments were not inside the cell, but outside the cell. We took a chamber. Chamber was filled with water and suspended particles or microspheres, little spheres. And into that suspension of microspheres in water, we immersed a small gel, tiny. So we put the gel inside, and we looked in the microscope. And what we found is we didn't even need a microscope. Actually, it was so prominent enough that you could see it with your naked eye. But we used the microscope, and what you could see is that in a region next to each and every surface of the gel, something was happening. It took a few minutes, and what was happening is that the microspheres were being excluded from the regions adjacent to the gel. It took 3 or 4 minutes, and this so-called exclusion zone, or EZ for short, easy to remember, but not in Europe where it's EZ. But anyway, easy. We called it EZ water because it excluded. That was probably a misnomer because it doesn't speak to the reality of what this water really is. It's different from what Gilbert Ling was talking about, and different from what anybody had thought. It's a different kind of water, and we found through experimenting using various methodologies, a dozen or so different approaches. Every measurement that we made of this water differed from measurements of liquid water. So then we began to call it fourth phase water because it didn't behave like liquid water. And so right now we refer to it either as fourth phase water or EZ water interchangeably. It's the same thing. Okay, so that's just an intro. And what we found, we started making a whole lot of different measurements, and we made an electrical measurement. And we naturally suspected that this zone, the EZ water, would be neutral because it starts with ordinary liquid water, which is neutral. So why would we? But I had a lot of experience with microelectrodes, parenthesis, invented by Gilbert Ling, by the same person, sticking in cells. And so we stuck electrodes into this water, knew the techniques, and astonishingly, we found that it was negatively charged. It didn't make any sense because you start with liquid water, which is neutral, and you wind up with something that's negatively charged. So what happened to the positives? Well, we found that they were present just beyond this EZ water. So you got a negative EZ next to positive water with protons or hydronium ions. So that constitutes a battery. So we found that this kind of water is like a battery, that it has separated positive and negative charges. It's kind of like like the first step of photosynthesis, which involves separating positive and negative parts of water. But in plants, the energy comes from light. Okay, so at the time we hadn't thought about this, but we couldn't figure out where the energy comes from. You know, to charge a battery, you need energy. Like if you don't charge your cell phone at night, it doesn't work in the morning. And so any and every battery needs charging. And so we wondered, and it took me. I spent a goodly amount of time over a couple of years trying to figure out where does the energy come from, and I was unable. And then, by chance, a young undergraduate student who knew nothing about, he was just basically starting his university career, and he was doing one of the experiments similar to what I just described that we had done. I forget what his question was exactly, but he was playing with this, and he noticed whether he was really curious or whether he was bored. He noticed a lamp that was sitting right next to him, one of these gooseneck lamps, you could bend, and he took it and he shined it on the chamber, and the region that was illuminated, the region of the EZ, grew by a factor of 3 times. And so he called me in. I took a look and I said, "My goodness, if this can be repeated, it looks like he finally found the source of energy. It was light, just like the first step in photosynthesis, but more general." And so we started to do real experiments to find out which wavelengths of the light were most responsible. And we found that it was not ultraviolet, it was not visible spectrum, it was actually infrared light. And a lot of people don't know where infrared light comes from, but for example, it comes from the sun, which, whose energy that we receive, 50% or so of that energy is infrared energy. And the warmth corresponds to the infrared energy. But more than that, everything is actually generating infrared energy, because if you turn off all the lights, for example, where you're sitting right now, and you can't see anything, and your cell phone camera can't pick up anything, if you whipped out an infrared camera that is a usual camera, but with, instead of a visible light sensor, an infrared light sensor, you get a beautiful image despite the darkness. And that's because everything in your background, including you and your chair and the wall, is generating infrared energy. So that's why the military uses it for night vision. Anyway, infrared is all over. Therefore, the energy that you need to build this EZ water is ample. It's all over. So that's how we started, and so that's really you might say, if I were to try to indicate one at least of the major uses, I would say, this energy, it's that the water actually can, in the right circumstances, can be a transducer that transduces light energy into different kinds of energy, and that exists in your cells. This water exists in your cells, and the reason your cells are negatively charged, and what I'm going to say differs from the standard interpretation. The reason your cells are negatively charged is that they're filled with negatively charged EZ water. Very simple. So, and that's a source of energy.
Wow, this is fascinating. And the way you talk about this, it's really interesting to listen, even for someone who had no idea about these properties and qualities of water. So we know in one of your presentations, you mentioned about collective properties of water and that water should not be considered as a single molecules. Could you please explain why? And what is the role of hydrogen bonds?
It shouldn't be ordinary liquid water can be considered a collection of single molecules. And each one is largely independent of the others. They do form hydrogen bonds, but basically they're more or less independent because they're randomly oriented and they fluctuate. They move around, they bounce around at a very high rate. So it's easy to think of them as single independent molecules, although, as you point out, that they do form bonds, or hydrogen bonds. Now, easy water is completely different. It forms a semi-solid mass of high viscosity. The viscosity is high because the molecules are actually sticking together pretty tightly. And the way they stick together is that next to the solid surfaces next to which they form layer by layer. And so the surface is able to nucleate this change from ordinary liquid water to EZ water. And the structure of the EZ water we found is a honeycomb structure, and that's consistent with X-ray diffraction results. So, and then this first layer, which is a hexagonal, then serves as the template for the growth of the second layer, which is the same as the first layer, and so on. And these layers build and they stick to each other, at least loosely. Now, not by hydrogen bonds, but by electrostatic bonds, we found. And these layers can grow up to hundreds of thousands of them. You can see it with your naked eye. You can see this zone because these layers stick to one another. Molecular bonds are extremely important, and as otherwise they wouldn't be sticking to each other. So if you contrast this structure with the structure of liquid water, they're completely different. And in fact, the chemical structure of this is not H2O anymore. It's H3O2. Now, if it were H2O, it wouldn't fit the evidence because the evidence shows that it's negatively charged, and H2O is not negatively charged; it's neutral, so it can't be H2O anymore. So it actually has undergone a chemical, you might say, chemical or physical chemical transition to something that is very well bonded. One layer is very well bonded to the next layer. So in response to your question, that's how we see the structure. And if you allow me, I might want to amplify on one point. Now, these sheets, these hexagonal sheets, are stacked one upon another, and they're actually displaced by half of a hexagon from one another. So you've got one layer, and the next layer will be shifted slightly, and the next layer shifted slightly. And what that means is that the holes, the hexagons, are compromised. If you want to get through a lattice like this, it's you have to be really skinny. It's really hard to get, and that's critical. Why is it critical? It's critical because I was talking about a battery where you've got negatively charged EZ next to positive charges. So you've got a battery, and we can actually draw current from the battery. We have proof of principle of that. But those positive charges don't want to be separated from the negative EZ. The positive charges want to immediately recombine, right? You got negative and positive. All they want to do is coalesce, like man and woman or something like this. They want to come together. And ordinarily, they would. It's really difficult to separate them. However, the positives, which are actually water, protons stuck to water or hydronium ions, they're too big to get through those holes, and therefore they stay separated. And this is a really important concept because otherwise you'd never get separation of positive and negatives. They always want to instantly recombine. So that's an important feature. Anyway, I think I went on to answer more than you asked. So
yes, but it's extremely important and interesting. So thank you.
Yeah, thank you very much. That's a very interesting explanation. Just I understand so you talk about the water, ordinary water, and this exclusion zones, like this fourth phase of water. But when we started to look at the ocean, it's pretty interesting how it is structured and organized. And I was really surprised, to learn that the majority of the water in the ocean is at 4 degrees C. So, it's essentially like the great depth it includes water at 4 degrees C. And I would really like to hear, and we know that this is the densest, the conditions that water has the highest density. So what are the properties you would consider that this deep water at 4 degrees C would have?
We studied what happens as you change the temperature. And we weren't sure. So our experiments are usually done at room temperature. And so a student in the lab decided to look and see what happens if you increase the ambient temperature and then if you decrease it. And we were most curious about the exclusion zone and what happens to it. And we found that as you increase the temperature, the exclusion zone, in fact, grows smaller. And we never published this result and didn't really focus so much on why that happens. But what was more interesting was what happens when you reduce the temperature. So we found that when you reduce the temperature, the exclusion zone increases. And when you reduce it further, it increases a lot. And when you reduce the temperature even further, it turns into ice. Now, ice also has a hexagonal structure, so it's not a surprise. And also this is very dense when you get down to the point just before it turns to ice. Of course, ice is not dense, and there's a transition between the easy water and the ice. And I don't need to describe it in detail, but it explains why ice is much less dense than water. You know, ice will float. So we found that it's a necessary condition. If you want to take water and form ice, you can't do it directly. You have to first form easy water, and then the easy water transitions into ice. And if you want to melt ice, the same thing in reverse occurs, that the ice crystal turns into easy water, which eventually turns into ordinary liquid water. So that doesn't necessarily explain why the water down at the bottom is easy water, but the density means that you'd expect that at the bottom of the ocean, you should have a lot of easy water. And, I'm stumbling because I haven't really thought about answers to your question, but I've alluded to a few issues that would be relevant to answering. And there is one other thing that could be relevant. I'm thinking out loud, and I'm thinking that there are geothermal sources that at the bottom of the ocean that generate light or infrared energy that could convert that water to easy water. And if it does convert it, the easy water has a low temperature because the molecules are not moving around at all. It's like a crystal. And we actually measured directly that easy has an effectively lower temperature than any other water. So if those geothermal sources are creating easy, then the temperature, effectively, temperature would be lower, would be low. And I think that could explain why the water at the bottom of the ocean tends to be at 4 degrees C, very low temperature, not converted to ice, but low temperature associated with the presence of easy water.
Professor Pollack, that's a really amazing explanation. And thank you very much for bringing this up because, part of our research is also we are studying these geothermal sources at the bottom of the ocean.
Oh.
And we see the evidence of the increasing of the heat, which is coming from the bottom of the ocean. If you're interested, we can share with you the most recent data. And in fact, like this geothermal source and this heat, which is coming from inside, it's really having huge influence on the ocean and seems to be on the properties. That's really amazing. Thank you very much.
Well, thank you for asking the question. Sure, no problem. You stimulated me to think.
Thank you.
Also, we are seeing that something is happening to the ocean worldwide. It's getting much hotter, maybe due to geothermal activity. And we would like to ask you how, based on your research, changes in pH or temperature affect water's properties. Well, since we talked a little bit about temperature, maybe you could tell us about pH.
Yeah, pH.
pH.
So let me start with an anecdote. When people, over a period of a couple of years, when people would come to my office to chat, and when we got to the issue of charges and pH and such, I asked them. I said, "If what do you think? If I tell you that something has low pH, it means that there's an abundance of hydrogen of protons in it. Does that have net charge or does it not have net charge?" Now, I'm not sure what how you would respond, but to summarize, roughly half the people said, yeah, it's because of those H pluses, a low pH. If you have some water with low pH, it means that that water has net positive charge. 50%, the other people say, no, 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 you can't have a glass of water with net charge. It's impossible. And just take, for example, HCl. The H plus is balanced by the Cl minus, and so there's no real net charge. It's just pH. So after having interviewed so many people and having found that that half the people say low pH means net positive charge, and the other half saying no, the low pH doesn't mean net charge, I drew the conclusion that nobody really understands what's going on there, and there's a lot of confusion, and they're not taught whether low pH means net charge or no net charge. The same with high pH, except that we're talking about negative charge. So we did a study and we published it. And the conclusion of the study was that if you have a low pH, it means you do have net positive charge. The correlation was practically perfect with measurements of net charge and measurements of pH. And the same or the opposite with high pH. So we found and published a paper showing that pH is really a measurement of charge. And pH tends to be, for some people, a little bit complicated to understand, but net charge is really easy. So it means if you've got a low pH, it means whatever is the liquid that you're measuring, it's got net positive charge, more positive charges than negative charges, and the opposite for high pH. So we produce what we think is now a simpler and better understanding of what the pH means. So in terms of ocean water, if the pH is dropping, it means that the water has an increased concentration of EZ water. Because whenever you have the EZ water forming, you've got protons that form. So I'm not sure if that answers your question, but it kind of alludes to a phenomenon that I think is really important to understand, that you got a liquid, and liquids don't necessarily have to be neutral. And the same with the ocean. It doesn't necessarily have to be neutral. If it's got low pH, it's got net positive charge. And then, we can speculate where those positive charges might have come from. And I will speculate, if the bottom of the ocean is filled with EZ water, whenever EZ water forms, protons are released because the water is transitioning from something neutral to something negative, and it's got to cast off protons. And so if the measurements up near the surface of the ocean show low pH, it means, or it could mean that the EZ water that we discussed in a moment beneath, near those geothermal vents, whenever that forms, they release protons. And if you make the measurement somewhere levels above those deep waters, you should measure net positive charge. Well, I'm not sure, because I don't know about the distribution of pH throughout the depths of the ocean, but at least this is something to think about.
Like I'm more about that. For example, if we take like we know about this ocean acidification, which is happening nowadays, right? And if we will just bring in the laboratory, like if you studied this effect that you decrease pH and how that was affecting easy water formation. And
Okay, well,
if you
let me,
go upper, uh-huh.
yeah. Now, so as you know better than I, the pollutants in the ocean are increasing dramatically. And pollutions are molecules of sort, and various molecules easily form layers of easy water around them. So you put in a molecule of, say, some pharmaceutical into the water, into the ocean, and surrounding that molecule coming from some pharmaceutical, easy water forms around it, as it does next to most, or not all, hydrophilic surfaces. So once that EZ forms and grows, it casts off protons. And this could be the reason for the acidification.
Yeah, I get it. So like I just was more kind of thinking that if we take into account this, I don't know, like this changes in CO2 absorption, and we kind of see that this external force is coming as acidification, then like how that is affecting. So
Yeah, but I think that could be
uh-huh,
the reverse of what
I
actually
get it.
happened. Yeah, so I'm
Uh-huh,
trying to get at
uh-huh,
what's the cause of the acidification.
yeah.
The consequence, you know much better than I do. I mean, the consequence of the acidification. But I'm referring to the initial cause of the acidification.
Yeah, I get it. No, that's very interesting. Thank you very much. We see that a lot of pollution of the ocean nowadays, and with the microplastic and nanoplastic. And it's that the scientists really the more precise instrument for measuring like the smaller particles we have, the more and more nanoplastic we are discovering. And like, could these microplastic and nanoplastic this affect formation of these exclusion zones, and what would be the consequences for ecosystem, for properties of the ocean, like for living organisms?
Well, yes. So the nanoplastics, microplastics, if their surfaces are hydrophilic, if they're hydrophobic, then no effect regarding no buildup of EZ. But if they're hydrophilic, then they might, a good chance, form EZ around them. And as I described a moment ago, outside of the immediate region of a particular micro or nanoplastic would be protons. And so those protons are basically filling the ocean, and they're free. They're actually in the form of hydronium ions, that is, a proton stuck to a water molecule, and they repel one another. The negative EZ is stuck to the particle, but the positive protons or hydronium ions are free in the water, suspended in the water, and because they repel one another, they're going to disperse and spread basically all over the ocean. And so, I think that's the reason. That could be the reason. I don't assert that it is the reason, but it certainly could be the reason why the ocean. Why the pollution is causing the ocean to become increasingly acidified. And for living beings that live in the ocean, I guess I could speculate that if the pH gets sufficiently low, they may have trouble coping with their existence. I've not studied that, so that would be a pure speculation. But how low does the pH get of the ocean?
Um, I don't think that it's more than zero point 0.1. So like I think it's just we are working in a buffer, right?
Well, why? You mean your experiments are in a buffer, or the ocean is?
No, 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 no. I mean, like the ocean is considered to be a buffer solution. So, and that is, I
Why?
think, like the acid changes. I think like there is like how I see it's at a bicarbonate carbonate equilibrium, and I like always considered ocean as it's not extreme changes. It's like I thought that it's about zero point 0.1 in pH changes.
Well, okay. I mean, I can imagine that because um, the ocean is pretty large, and so if these positive charges that I'm talking about are free and released, they're going to disperse all over the ocean. So the concentration of positive charges is going to be pretty low when because of this dispersal. And so that would be consistent with the observation of only a 0.1 change of pH. Whether that has a biological effect or not, I'm not sure.
Yeah, thanks a lot. I'm really appreciating your openness. Like another thing is that what is interesting is that I know that you were studying this, how this minimal amount of substances may affect the properties of water, and like this like homeopathic amounts of these substances. How does it work? How does it change the properties of water? Like, what is the mechanism for that?
Okay, well, yeah, that is something that we've given some thought to. The homeopathic phenomenon means that there must be some kind of memory in the water, because if you dilute and dilute and dilute, eventually, or statistically, you have only water that's left. Now, the original, I wouldn't say the original experiment, but an experiment dealing with water memory and the homeopathic dilutions was carried out by a guy named Jacques Benveniste. Perhaps you know the name, and and because of the implications that the water could have memory, uh, he basically lost his career and he died prematurely. So let me just say about his experiment, his homeopathic experiment. So he found that he was studying some cells that secrete histamine. They're called basophils, names of the cell. And he demonstrated that if you put certain or expose those cells to certain antibodies, um, they will secrete histamine, a very specific kind of reaction. And someone came and said, hey, I can show you that I can dilute those antibodies um, to the point where there's no antibodies left. It's just water that had been exposed to the antibodies and produce the same result. He said, impossible. But he said, he was a very open-minded guy. He said, okay, there's a corner in the laboratory of 50 people that's not occupied. Show us. So he demonstrated that, and they were simply amazed. And so they pursued the subject in more depth, and that led to ultimately, I think, his demise. But the point is that there must be some memory in the water of the original, in his case, of the antibodies, of the original antibodies. Otherwise, it shouldn't work, because otherwise you're exposing those cells to pure water, and the secretion that occurs is very specific. So he got intrigued, and as I said, that's what led to his rejection by scientific society. But so one of the issues in that, and one of the reasons why people couldn't believe that this was the case, is that ordinary liquid water, the molecules are bouncing around furiously, and they're disorganized. And it's hard to imagine that that kind of water could store any information. If you think about how information is stored, let's say for your laptop computer, let's say in your thumb drive, you see a plane in which transistors are distributed at regular points on a grid. So you got transistor, 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 et cetera. And each transistor could be either on or off, like 0 or 1. And it's the distribution of zeros and ones, on, off, that store the information. So the analogy is maybe you need a kind of water that has this sort of property where the molecules are regularly distributed over a plane or multiple planes. And at least one of the elements present in each plane has at least two different states. Well, easy water is just like that. It's a plane of hexagons consisting of oxygens and hydrogens. And it turns out that the oxygens have 5, not 2, but 5 different oxidation states or charges, or whatever. The usual one that we know of is -2, but there's also -1, 0, +1, and +2. So it satisfies the easy layers satisfy the criterion, or they could mimic what computer memories are able to do, except because we're dealing with the atomic scale rather than the transistor scale, the information density could be extremely high. So we think, this is tangential, that one day it's possible that computers will be the size of pinheads if the substrate turns from transistors to easy water. But at any rate, I think this answers the question that a lot of skeptics have about the homeopathy. The skeptics will say, well, if you dilute and dilute with water, eventually all you have left is liquid water. But that's not the case for easy water. And so it's possible, if there's easy water that exists, and when you dilute and then you shake it or succuss it, and you have little clusters of easy water because you disrupted the overall structure, that those disrupted clusters, whatever, there are so many of them that when you dilute 10 times or 100 times, diluted water will contain them. And then they may grow and grow, and you dilute again, and still some will be retained. So you could do, theoretically, an infinite number of dilutions and still have some, quote, memory, because the memory could be stored in the EZ. So that's my take on that subject. And perhaps having a Russian background, Alexander Konovalov. No, he produced the most extensive results I've ever seen on what happens during high dilutions. And I guess all I want to say about that is he was the rector of Kazan University for 11 years. And his stuff is in Russian, and some of it is in English too. It's fascinating. So anybody who's interested in homeopathy and the mechanism underlying it, read his stuff. So
thank you so much.
Yeah, sure.
And since you were talking about the delusion of water and water memory, it reminded me a little bit some articles I read about 20 years ago about Masaru Emoto's Japanese experiments that he was doing. Could you comment on those? Were you
Sure. Well, I know those people well. I'm invited every few years to come to their office and make presentation to various people. So unfortunately, Masaru Emoto died about 10 years ago, and I never met him. If your listeners don't know about his work, he would put his intentions or project his intentions onto water, and then he would freeze the water. And if his intentions were positive, like "I love you" or "peace" or something like that, then when he looked at the water crystals that formed, they were beautiful. And if he had if he cast negative attention, they were ugly. He did the same with music. If he played a Bach cantata, the crystals were beautiful, and heavy metal produced ugly crystals. So he was not a scientist, he was a spiritualist. And so scientists tended to reject his ideas, and especially because it came to their attention that he would cast his intention to, say, 50 different petri dishes full of water, and he'd examine all 50 of them, and he'd pick out the one that looked nicest or best to illustrate what he wanted to illustrate. And he maintained that he was not a scientist, he was a spiritualist, so that was acceptable. But scientists didn't accept it. There was a study that was conducted by a guy named Dean Radin, who showed that actually a disinterested audience could pick out the positive ones from the negative ones. Statistically, it actually did work. But at any rate, his work is so interesting, and the implication of it is that there's some kind of energy that comes from or consciousness or intention, and that energy is found in the water. that the water is somehow impacted by that intention. And I think his work has made a real impression on so many people. His book, and the second one just came out recently. But the first book sold many millions of copies because people were fascinated by it. And right now, his work is being extended not only by the group that still exists there, but by a woman named Veda Austin, who is doing similar stuff with a slightly different technique. Again, the water memory is the idea. And I remember when she was starting her career, she came to my home, and we sat down at the kitchen table, and she put some water in front of me, and she said, "Think of something. Don't tell me what it is, but think of it." So in this container of water, I thought about a house. I didn't tell her that. And she took the container of water, put it in the freezer, took it out 10 minutes later, and there was just a thin layer of ice on the top. And on that layer, you could see a roof. I mean, you could see something that looked like a roof. And she's since produced, I wouldn't say millions, but thousands of images that demonstrate, for example, if she, I think it's on her website, she puts either beneath or above the container of water a piece of paper with the number 4 written on it, and she puts it in the freezer. And sure enough, on that layer of ice, you can see the number 4 clearly written on it. That's the kind of experiment. So yes, Masaru Emoto was the pioneer, to great acclaim, and also to not such great acclaim among the scientists. But there's something going on there. The idea that intention contains a kind of energy that probably we don't understand, and it's creating, it's doing something. And the field is right now is of that water memory is really at its infancy. Nobody knows. Just like 300 years ago, if you had, or even 200 years ago, if you had talked about electromagnetic energy, people would look askance. What the hell are you talking about? I never heard of such a thing. And then came Maxwell and such. And so there may be yet another kind of energy that we simply don't know about and that exists. Apparently, that seems to be the case. This is a frontier issue in science, which is now largely ignored except by a small group of people. Hope that answers your question.
Yes, thank you.
Yeah, thank you very much. That is very interesting example and a really great question. So, I wanted to come back to the topic from your TED talk, and you mentioned about the role of the electrical charges in the atmosphere for the formation of the clouds, and how these clouds are formed. So, what could you please describe this process, and what are your understandings about that? And maybe you did some more research on that.
Well, I did some more thinking about that, and the thinking will appear in a book which is due out March.
Congratulations.
Called Charged, and it deals with charges in clouds. It also deals with charges in other phenomena that we see every day, we witness, but we think we understand them. But if you dig slightly, even one layer beneath the surface, you find that your explanation doesn't fit. There are anomalies, many anomalies. And so I treat not only clouds and weather in that book, I actually make an attempt to understand from first principles how weather occurs, how clouds form, why you can get a hurricane, et cetera, et cetera. I also deal with gravitation, which we all think we understand, but not everything fits. And there's some more to it than, at least I believe, than what we think. I deal with how birds fly. If I were to ask you how do birds fly, you'd probably say, well, they flap their wings. But there are certain birds which I can see out my window, like eagles, which may flap their wings on occasion, but mostly they fly perfectly well without flapping their wings. And they can fly for long distances without losing any altitude. Sometimes they even gain altitude. They can go into the wind, against the wind, with the wind, right angles to the wind, doesn't matter. It happens every day. So there's something more than just flapping of wings that occurs. And the same with sailboats. It's easy to understand how sailboats go downwind because you put out the sail and it catches the wind, and the sailboat moves downwind. But sailboats also go upwind, and most sailboats can go up to, for example, maybe 45 degrees off the so-called apparent wind. But racing boats can actually go closer to the wind, maybe uh, uh, 25 degrees or 30 degrees. They're like sailboats on skids, and and they go almost directly into the wind. So if you're sailing one of these boats, you feel the wind on your face. They go really, really fast. 100 miles an hour is not atypical. So you can imagine if I'm blowing strongly at you, and you'd expect through everything you know about physics, you're going to go back, not toward me, but away from me if I blow on your face. But in this case, these boats go in the opposite direction. And the question is, how do they manage it? And so I deal with that in the book as well. But charges are really important. And in cloud formation, charges are practically everything. So, if you're surrounded by foul weather and thunderstorms, you know that some clouds have electrical charges. But it was found long ago, but, not currently considered to be important or relevant, that all clouds are actually charged. So if you look at a cloud, which I'm looking at right now, the question is, how do they form? What's going on there? And what we found is that charges are critical. So the clouds, the cloud is not a solid and it's not a liquid, right? But what is it, and what keeps it up where it is? Well, what the cloud is, it's a collection of little droplets. And what we found in our studies is that each one of these droplets has a net negative charge. But you'd expect that those little droplets would repel each other and never form something that looks like a cloud, because the droplets are somehow held together. And we found that they're actually held together by intervening positive charges. So you have two negatively charged droplets and a positive in between. And it reaches a kind of equilibrium when the attractive force of that positive charge is balanced by the repulsive force of the two droplets. Then they're stable. And this is not an original idea. It comes from Richard Feynman, the great Nobel physicist. He called it like. That is, like charges, the two negative charges, they like each other, so they want to come together. He said likes like by intervening opposite charge. So I think he didn't say that that's how clouds form, but this principle that he was talking about, I think, underlies the formation of a cloud. Nobody really understands, how clouds form. Or what goes on. And I think that Feynman's idea is not only relevant, but critical to an understanding. So you don't need many positive charges. You need a few next to these negatively charged droplets, and then you've got a cloud. And of course, if you have more positive charges, these will come closer together. If you have fewer, they'll be further apart. And that's the basis for understanding how you got different clouds. The question that comes immediately after that is why, if these droplets are heavier than water, heavier than air, they should come down, right? But the cloud stays up usually. Why? And I think the answer is that not only is the cloud negatively charged, but the Earth is negatively charged, and so they repel each other. So you can understand why sometimes you see three clouds stacked upon one another, one low, one medium, one high. It depends on how much negative charge they have, how much repulsion there is from the Earth. And so what causes rain? Is there some magic gremlin who sits inside the cloud and turns the switch and then the rain falls? Well, no, that's not what it's. If the cloud has, well, let me say, the droplets are actually pulled to the earth. If a cloud is low enough, its charge will induce opposite charge on the surface of the earth just beneath. And by virtue of these opposite charges, the earth can't move up, the cloud will move down. And the induction gets more and more powerful. And that's what pulls the droplets of rain. And it was shown that it's not just rain is falling droplet, because you can calculate based on the size of the droplet the terminal velocity that should exist if the droplet is simply falling. And the measurements have shown that the droplets descend up to 10 times that expected velocity. So something is pulling the droplets, and I think it's this induction force that grows stronger as the cloud gets lower. And ultimately, the force is so strong that it pulls down. That's why you can get pounding rain. I think I've gone beyond your question, but I wanted to talk about that a little bit.
Thank you very much. That's a really amazing explanation, and I would be really waiting for announcement about your book. That's a very, very cool thing.
Well, I'm also waiting for an announcement. It's my son, who's a gifted artist, who illustrates the book, and he's a fantastic artist. That's why the Fourth Phase book has received so many accolades. It's not due to my ideas or my writing, but it's due to his fantastic artwork. But we're thinking that it should be March.
That's
and
great.
I'm excited.
Yeah, congratulations, because like we are like, it's also like, as we are doing like this holistic observation what's going on the planet, we do see that there is no real explanation for clouds formation. And what is recently one of the phenomena we are observing is that the clouds are getting more closer to the surface of the earth than before, and no one could really explain that, what is going on.
Oh, really? They're getting closer.
Yeah. Yeah, and another thing, just like that's really, it's just like, you bring so much stuff. Thank you very much. I really appreciate it. And it's that, also we are, since we will, in our ocean movie, we talk a lot about the microplastic. It also seems to be that microplastic playing also crucial roles in nucleation, and it also may drag these clouds down. But it's just, I think there is also overall this electrical processes, or like this, I don't know, like the processes related to the charges on our planet, they are changing so drastically that it's just really like it's cascade of changes, because there is like the enormous increase in lightnings, not only lightnings which is going like down, but also all this like all these how do you call this, red sparkling things which is like charging into the space. So like all these like charging phenomena, they are changing a lot on our planet, and I think your book is timely.
Well, what you say is new to me and interesting. And if you have a cogent hypothesis for what's going on, which I hope that I'm presenting in this book, then you have another basis for understanding what might be going on. For example, to create the cloud lowering and increase in, you say the lightning is increasing too? Yeah.
Absolutely.
Well, so charges are inevitably related to lightning, and I think the charges are centrally related to clouds also. Cloud lowering for me means that the negative charge, or one possible explanation is that the negative charge of the cloud is somehow increasing. One would have to speculate why that might be the case. There are a few possible reasons, but the pollutants could play a critical role in that, because of the formation of easy water around them and the charges, the separation of charges that result. It offers an opportunity for well-developed hypotheses that could be tested. So it's exciting for me to hear that, because I haven't followed the story very much.
We had to conduct interviews with everyone we could because we wanted to find out what's really going on. Like, that's the main driver of our activities. And what we learned is that evaporation of water from overheated ocean, it takes into atmosphere massive amounts of also nano and microplastic particles. And the biggest amount of nanoplastic particles were found not in fields or urban areas, but in rural mountain areas where there is virtually no human presence, but the rain takes this human pollution to those areas. And apparently, because there is no circulation or amelioration of those areas, they stay on top. So when we started asking all the scientists, everyone we could, how could we possibly clean up the ocean water and atmosphere? One of the proposed solutions was to implement on a global scale atmospheric water generators. Yeah, so machines that basically generate water from moisture in the air. And because of overheating of the ocean and atmosphere, there is extensive amount of moisture in the air. So that way we could not only produce enough water for everyone, avoiding desalination and other not so clean sources of water, but also reduce the amount of this pollution particles in the atmosphere. But one of the main reasons why atmospheric water generators and filtration system in them are not being implemented globally is, of course, they consume a lot of energy. And here is where we come into an interesting point. You said that easy water, is capable of generating electricity. So I would like to basically come back to what you started from. And if you have something to comment on what I just said, please do. But also, how do you see energy production, and how exactly is it possible to use easy water as energy source? And how exactly it generates energy?
Yeah, okay. So your discussion actually produced a whole lot of issues and questions, but let me just respond to the last one about energy production. So as I described in the initial experiments that we did with water particles and inserting a gel or a polymer or a biological surface, it doesn't really matter as long as the surface is hydrophilic. So you have the formation of the EZ, and EZ has negative charge, and the region beyond has positive charge. And so we, or one of my students, Kurt Kung, put electrodes, one negative and one in the positive, and he hooked it up to an LED lamp, and he turned on, and voila, the lamp lit. So it's clear that you can actually draw current from this battery, so to speak. It really works. And the question is whether this can be scaled up. And we don't know the answer, but we think there's a possibility. Now, if it could be scaled up, you could imagine all it requires is water and light, water and infrared light. It doesn't deplete the earth of valuable resources the way that ordinary semiconductor like LEDs do, which is basically water and infrared. And so we're thinking that this could, since we have proof of principle now that it works, could be buildup could be tested to see whether the amount of energy that's produced could, for example, power a house with essentially nothing. Just some water, which is pretty abundant, and infrared energy, which is also abundant, or even power a city. The world is really short of energy. It's becoming increasingly scarce, and so we think that it's possible that this discovery of EZ could ultimately lead to a new class of energy suppliers. Now, so that's one. There are other issues that you were raising, and let me say that although this first issue that I was talking about is fully described in my book, The Fourth Phase of Water. Maybe that's why it's as popular as it is. But the new book talks about, as I mentioned earlier, about cloud formation and such. And we found that there are two components of negative and positive charges, which I mentioned, and they come from different aspects of evaporation. So mainly the evaporation or the production of these droplets of water comes from evaporation of huge clusters that form and that rise up out of the water. And it's too much to describe that here, but the Fourth Phase book describes it rather completely. There are some astonishing observations that we made that support our contention that these big blobs of water are rising. Now, the blobs could contain all kinds of pollutants. This is a possibility. And so that might explain why there are an increased number of pollutants in the clouds. I had not thought about it, but this is certainly a possibility. The other aspects are protons or positive charges that repel each other and therefore are forced to escape from the water. And it's a combination of those protons and those big blobs come together that form the clouds. So I'm responding to your statement, which I had not known, that the clouds have an increasing number of nanoparticles or microparticles. And I think that's where they come. They come from evaporation, which is not, as the textbook describes. Textbook says that molecules of water acquire a certain amount of kinetic energy or potential energy. They get kicked out of the water. That's not what we found experimentally. And as I said, it's described in the Fourth Phase book. So I think there's truth in it, but it's for the reader to decide. So I tried to respond to a couple of the issues that you raised.
Thank you. Well, one of the things we're noticing, because we not only study water, but trying to understand what is happening globally, we're noticing big changes in the magnetic field of our planet. The rise of South Atlantic magnetic anomaly, it's growing inside. We're seeing overall weakening of the magnetic field of our planet. We're seeing more strange, even red auroras closer to equator, which was considered April Fool's joke 10 years ago, but now it's reality. And we're seeing the anomalously strong magnetic zone in area of Siberia. And that is exactly the point to which northern magnetic pole is shifting. So in this sense, we cannot ignore the fact that it might affect water as well. And maybe in your studies, you could share with us something about magnetic field and its effect on water.
Yes, we just published a couple of years ago. If you insert a magnet into a chamber of water with microspheres, the microspheres disappear from the region of the North Pole and the South Pole. So it looks like easy water is being formed by the magnet, both at the North Pole and the South Pole. And recent experiments, not yet published, shows that once these zones are formed, if you put another magnet nearby, it kind of pulls the blob of easy water. It forms a kind of amorphous structure, but it shows that it's all held together the way we expect it's going to be held together. And you can, pull on it, and just like a gel, for example, if you take a raw egg and notice that the cytoplasm is not water, it's a gel, right? And you can take it and pull it. This region behaves in exactly the same way. Now, as far as the understanding of magnetic fields, I deal with that in the book that's coming out. I'm not sure how much I should mention because without being able to back it up, it will come across as so radical as to be even preposterous. But I'll just say, I argue that magnetic fields may actually be the same as electric fields. Let me just leave it at that. Anybody who's interested, please have a look at the forthcoming book and see if my arguments are cogent or not. So I don't know why it's shifting over time. we think of the Earth's magnetic field as arising from the core of the Earth, but nobody's ever been down there, to check out what exists in the core of the Earth. And another possibility is that the magnetic field of the Earth comes not from the core of the Earth, but from currents that are flowing around the Earth. So everybody, the students of electrical phenomena know that when you have a current flow, let's say in a wire, then you have a magnetic field that runs around the wire. Well, the possibility exists that that currents flowing from space onto the Earth are actually responsible for creating the magnetic field. That obviously flies in the face of what everybody believes. But once again, if you want to read the arguments, please have a look at the forthcoming book.
Thank you very much. And I think, in fact, it's that there are beliefs that there is like both influences for magnetic field formation, both from inside and the atmosphere, also like forming this extra contribution to the magnetic field. I think that's really interesting topics what you're bringing up. Like I don't know, just for me, is that if you really want, I don't just like I wanted to ask you if you will have any thoughts on this, how this microplastic may change the properties of water, because like the deeper we are digging, we kind of like now lifting a lot of literature which is relating to that, especially nanoplastic. It seems to be extremely harmful to the cells. It's really like disrupting a lot of properties. And like if you have some thoughts how that works and would like to share, like even later, we would really appreciate it, because it's like it seems to be really unexplored area, but we see that it might be one of the major contributors, and it seems to be that it's like kind of having this not only toxicity but also disruption, huge disruption on the properties. So, and I think I want to ask some final question to you. And if you want to share some more thoughts on this microplastic, how that,
Well,
what the effect of that.
you intrigued me about this, and I think step one is to find out whether these micro or nanoplastics form easy water around them. Because if they form easy water, then inevitably there have to be protons reducing the pH, and that could be an important effect. And I know that we've studied and published particles, various kinds of particles that do build easy water around them. That's published, but we're never able to go down to micro or nanoparticles because they're difficult to observe. But if studies could be done to see whether these form easy water, then we know that when easy water forms, protons form beyond the easy water. And that would be step number one, to try to figure out the effects, including the biological effects. Now, the biological effect could be, in biology, certain considerations lead to the idea that the solids inside the cell are the nucleating surfaces for the growth of easy water. That would be natural. And if you have something that's different from the natural proteins and nucleic acids in the cell, they may build easy water, and the easy water may or may not build easy water. And see, if they don't build easy water, then this is a problem, because it means that around each nanoparticle will be not easy water, but ordinary liquid water. And the cell needs, and this is a separate argument for which is difficult for me to present evidence, in this discussion, but we have ample evidence that each cell is filled with easy water, and it's a necessary condition for health of the cell. And if you don't have enough easy water, then the cell is dysfunctional. That, if anybody is interested, I wrote a paper on cancer and water that argues the case that the reason the cancer cells are dysfunctional and keep dividing has to do with the lack of easy water, extreme lack of easy water in those cells. So, that's a slight digression, but if some of the particles that you see in the ocean disrupt easy water, then it's going to affect the cell. The cell will become partially devoid of easy water, which will impact the health of the cell. So all of these things are tied together. You start with basic existence of easy water and go from there, and projects in all kinds of different directions, biological, geophysical, et cetera. I'm right now working on a book on volcanoes and earthquakes, and I think the water is the critical agent there. Again, without going into, there's too much to discuss in a simple interview, but that book will come down the line. I'm preparing 4 books and limiting factors.
Yeah, thank you, Professor. Like I just kind of like the thought if we have on the bottom of the ocean this easy water and microplastic would be something what disrupts its properties, then it really sound that it may also mess up like the like overall the functions of the ocean what we have. So just
Absolutely. Absolutely. The ocean wants to be devoid of contaminants. You just never know what these nanoparticles and such will do. So it's necessary to get rid of them. And in fact, just I might say, we developed a filter to get rid of nanoparticles and other agents. And we've been working on it, and we've progressed quite a ways. It's very simple. It has no physical filter. The separation has occurred because the environmental energy produces easy water. So the input is water with pollutants, and the output is easy water. And we collect the easy water, and it's essentially free of these pollutants. So we've come a long way of developing it, but funding issues are a problem for us. And in Seattle, the day has only 24 hours, and we have only a limited number of people working in the lab because the funding, for anything that's revolutionary, the funding is really difficult. We've been blessed from time to time, and I'm hopeful that we can be blessed soon again. But that's a limiting factor. And what you're bringing up is so critically important to study and follow up.
thank you. Thank you very much.
This is incredible, and this might be so important that humanity don't even recognize yet, just because the threat of nanoparticles and micro nanoplastic is not even fully realized. It's whenever we see in the studies, we see that they only started being published within the last maybe 5 years, and the data collected was for previous 5 years, and they're becoming more and more alarming. Like every month, every year, we're seeing that they reveal something that was not considered to be a threat.
I myself thought that the nanoparticle issue is something very recent, but it's probably been occurring for many, many years. So we certainly should be aware of that issue because we got to save this planet.
Absolutely. And that is a great message. One final question before we part is actually, what do you think in the properties of water, what is the most mysterious to you? What water's nature remains the mystery? And what, in your opinion, is the most underappreciated property of water in modern science?
I think that the most underappreciated, there's so many, is that water can hold energy. This battery-like effect that I was talking about. And, if you read a textbook, especially ones I look at, the biologically oriented textbooks, they regard water as merely the background carrier of the more important molecules of life. But everything we found said that, no, that's not true, that water is absolutely central for everything in life, and particularly the energy. We don't know, well, where does your energy come from? So if you know a little bit about biology, you say, oh, everybody knows that the energy is chemical energy coming from ATP. In 1941, a guy named Lippincott produced a paper showing that the energy that enables you to run a mile comes from ATP, which ultimately comes from food. But some people don't eat, and they can perfectly well do what other people do. They're actually, I found out from someone who was the central agent in in all of this stuff. A woman called Jasmuthine, who lives in Australia, she said there are something like 200,000 people who don't eat. Where does their energy come from? Because the idea is the energy comes, chemical energy makes ATP, and the high energy phosphate bond one of the phosphate bonds in ATP has high energy, and that's the source of our energy. On the other hand, at least 3 or 4 papers came out saying, no, that's not true. One of them, the first one, was a paper which I can't find, but I heard about from Gilbert Ling. It came out 1 year after the Lippincott paper showing that ATP had high energy. And these people showed or suggested that they made an arithmetic error and there's no high energy phosphate bond in ATP. Then there were subsequent studies that actually looked at ATP and found experimentally that there was no high energy phosphate bond, that the phosphate bonds in ATP were just like any other phosphate bonds. So there's been a series of papers that question whether the energy could actually come, your energy, my energy, could come from ATP. And that issue, it desperately needs follow-up because we don't know what's true and what's not true. Is it really ATP or is it not ATP? And if it's not ATP, then what else? Where does the energy come from? Well, I've presented a possibility that at least some of the energy, at least some, maybe more, could come. It could be electrical energy derived from the water, and water is everywhere. So this kind of energy is everywhere, and it's in the ocean too. So I guess that would be my sort of final remark. More generally, it is, don't believe everything you read in the textbook. My own view of that is that I would regard a textbook mechanism as being correct in either physics, chemistry, biology. Correct if it's simple and if it makes sense. If I could explain it to a barmaid, in 5 easy sentences, then okay, it's probably correct. If it requires twists and turns and further assumptions and whatever to explain, then my first thought is it's probably wrong. And therefore, I find myself not fearful of questioning many aspects that we consider textbook knowledge, but is it right or is it not? And the next book in line deals with the structure of the atom. And everybody knows that, well, the structure of the atom, we know what it is, even modified by quantum mechanical effects. It's got a positive nucleus and negative electrons and shells. Well, I start off the book by showing that there are some fundamental flaws with that, fundamental flaws that even a middle school student can pick out, and then go on to suggest what might be a better model of the atom. So what I'm trying to say is that everything we think we know, we may not know or might not be true. Some exceptions, but I start with that hypothesis. You might call it the Occam's razor hypothesis. It's got to be simple. If it's not simple, then it might be problematic. So I think maybe, is that a good place to end?
Absolutely. Thank you so much for being with us. Thank you for your openness and for sharing these incredible thoughts with us. Dear friends and viewers, today with us, we had an amazing guest, Professor Gerald Pollack from the University of Washington, and we were pleased to have you with us. Please share your thoughts in the comment section below, subscribe to this channel, and make sure to read the new book. Thank you for being with us, and see you in the next episode.